hit click here. And you should program on your laptop.
It's a recording. That shows it is recording. Yes, recording on the right side.
Yeah.
Yes.
Okay. But, so in case it was not recording before, let me just repeat. I will more or less start from scratch, introducing concepts in the beginning at least that are probably well known to many of you. But I will do it in some detail, which of course you will find in or hear about in a lecture in the course, mathematics course on category theory or other courses, but typically you will not see all of that in introductions to category theory for condensed mathematics. And at some point I have to use stuff which would take too much time to explain. So I assume you have some knowledge about group theory, representations of groups, and maybe, some a little bit homological algebra maybe, but in case I use anything that you're not familiar with, please tell me, and then I can try to explain or look it up, because it might be something that I don't know very well myself. So there will be a first very long section which is about categories. And these have several subsections. At the moment there are 12. I thought it would be maybe 4 or 5. They are the subsections are have very different lengths. Some are long, some are just 1 page in my notes. That's because when I started, I had a hard time to decide what to do in which order. And then I made a mistake. I decided to label or to number sub-statements and definitions by section and not by subsection. I will give these numbers. When you have any concrete questions after the lectures, if it's about something, just tell me the number you're talking about. So the numbers will go beyond 100 in each, at least in the first section. I should have maybe did it by subsection. Anyhow, then there will be a second part, which is about monoidal categories. And the third part about module categories. And then a part about higher categories, essentially only 2 or bi-categories, but I will also make some comments at least on double categories, again level 2, but most probably not higher than 2. And then there will be what you might call applications. So there will be some specific topics, mainly from work in which I have been involved myself. So this will be in particular the construction of correlation functions for two-dimensional conformal field theories, rational two-dimensional conformal field theories in the first place. This involves some will require some background knowledge from about conformal field theory. I will try to summarize this very briefly. If you're not familiar with those things, some of the statements I will make might not be clear to you why they are of interest, but I think we will nevertheless be able to understand it. Okay, so let me see, is there anything else No, I don't think I have to say more. So we will start with chapter 1, categories. In the first subsection, which is short, is about motivation. And the reason to try to understand categories and their properties and structures in categories is simply that they are there. And they are there everywhere. They just provide a language of speaking about things. And not only in mathematics, but also in physics. Very concretely, the results on conformal field theory, I will partly describe, have been developed by trying to understand certain observations or common law in quantum field theory and trying to make it precise, and then you're automatically led to the use of categories. And then there are many concrete, specific motivations. Originally, categories were developed in abstract topology partly, and then many more possibilities. But if you want to know about some of them, just look at the Wikipedia page on categories. They have a list of motivations. Then, for me, as I said, they are relevant in applications. For example, in two-dimensional conformal field theory, in topological field theories, then for their use in topological basis of matter. And that's all for general motivation. Before I start with the definition, which will already be in section 1.2, let me give a concrete example, and this is number 1.1 then. Where one is, which leads one to introduce, we like the concept of category, because it was not introduced in this context, but a general area where you quickly are led to use categories and also higher categories is when you deal with certain geometric systems which are related to manifolds and cobordisms. And I will actually introduce them in some detail later. But let me start with something which is maybe the simplest possibility, simple situation of the type. It's even so simple that usually you would not care about it probably. And this is simply that you look at compact-oriented zero-dimensional manifolds. Let's call it Y to have a name. So this will be a compact-oriented zero-dimensional manifold. Well, what is this? It's a point, but oriented, so I can have a positively oriented point, and I can have a negatively oriented point, and I can have collections of them. So disjoint unions. Let me draw them like that. And then you can relate two such objects, say Y1 and Y2, by one manifolds or arrows. Oriented one manifolds So assume I have a collection of 4 points and another collection also of 4 points. So this would be y1, this y2, and let's take the orientation plus, plus, minus, minus, and here plus, minus, minus, plus. And now I draw a one manifold which has these individual points as endpoints. So, for example, I have an interval-oriented interval here. I have one here. I have one here, and I have one here. And I also allow for closed circuits. You will see why. And there is a rule for what you are allowed to do. An interval will always start at a positively oriented point and end then at a positively oriented point. And here I already made the first mistake. Or it starts in white. Well, it's oppositely oriented and you have a negatively oriented point, or when they belong to the same zero-dimensional manifold, it goes from minus to plus, respectively, from plus to minus, respectively, from minus to plus. And now, with such configurations, let's call them configurations of arrows, you can do stuff. In particular, you can concatenate them. Let's assume we have one of them. It's more or less the one that I've drawn here, and take another one where we take here y1 prime, which is equal to y2, and then y2 prime. And so this is the same. And here, let's take one consisting of just 2 points. Oriented. Well, I don't write the orientations anymore because they follow from the rules that I have given to you. And assume here you have this configuration. And then there's only one possibility here. And now you can say you take the pair of these two configurations and you map it to what you get by connecting these points. I should have said that when we draw such arrows, we do not care about small variations of these lines, so they do not play a role. Also, there is no meaning of the lengths. We just think of this as, well, we could formally introduce an equivalence relation and say these arrows are equivalence classes, but I think it's rather obvious, so we will not do this. So if you compose them, then you just connect them according to the way, just identify y2 with y1 prime. And you see what can happen is that closed curves arise in this process. Therefore, well, this is one reason for allowing them in the first place. And then also there is a distinguished configuration. Of arrows which where I have y2 equal to y1 and all and there are no closed curves and no curves of this type. So they let me just indicate this schematically. All of them are just intervals which are parallel, and then with an orientation corresponding to the orientation of the points, zero manifolds. And now we claim that this is of some interest, and therefore we would like to have a concept which has this as an example. And the relevant possibility is notion of a category. Actually, in this example, we have more structure than the one of category. So I will come back to the example later on. So all these observations here we somehow want to formalize. Well, first of all, there's a two-layered structures. We have the zero manifolds and the one manifolds. We have some kind of composition, and we have something which is distinguished, which is, well, if you compose this, if you glue this together to anything else that fits, then by the rules that I mentioned but not wrote down, you see you will get back what this other configuration started with. So this is a kind of identity. And the same structure you find in many more situations. And then you define the following. A category, I generically denote it by some letter C or V or similar. Consists of the following. We have the following data. First of all, there is a class of things that we call the objects of C. And there's another class of objects which we call the morphism of C, and I will use the notation hom of C. Some people call this also arrows, as motivated, for example, by these examples. And then we have four maps between them. First of all, there is a map which we call identity. This goes from objects to morphisms. Then we have two maps S and T, which you can think of source and target, which goes in the other direction. So for each morphism, there is a source and a target, which is an element of the class of objects. And then there is a partial composition, which takes two copies of the morphisms, takes their connector product over the objects, and gives you again a morphism. And this is only a partial composition, and this is, by the way, one reason I prefer this definition here. We don't have to talk about that at this point. We will need some notation and conventions to the definition, not completely, such as the data. We need also some axioms that these data have to satisfy. So some notation. The notation here is actually not ideal in some respects. So we take some abbreviations. When we say we have an element of this class of objects, equivalently, we simply say that X is in C. Then if we have, say, V and W in C, in this sense, then we say that the homs in C, morphisms in C, from V to W are just those morphisms in the class of all morphisms for which start at V and end at W. So S of F is V and T of F is W. And we will actually later on, or very soon, require that these are actually sets, but I haven't talked about class versus set. We still have to do. Then, when I apply this map here to some object, instead of writing this in brackets like for a map, I write identity with V as a subscript. And similarly, if I take this composition, if I compose F with G, I write it as G after F in the usual way for composition of maps. And then also, if I have some F in such a subset here, first of all, the C I will leave out whenever it's clear what category I'm talking about. So, for example, if there is only one that I'm interested in, and in this situation, I will also write that F goes from V to W, so a notation which I use from maps, or also write V goes to W via F, and anything else? No, that's for now everything. And we say this is a morphism, as I already used, from V to W. And now I will use these notations in formulating the axioms. First of all, that's what I just said. For all objects V and W, this in principle class of objects is a set. And I will have to make a few comments on that a bit later. Then the terminology that I have used is sensible, meaning that if I take in particular the starting point of the identity of V, then this is V and also the target. And then this has the property of identity. So the identity for T of F, for any F, composed with the identity composed with F, it's the same as F, and this is the same as F composed with the identity of S of F. For all F in any morphism. This is identity axiom, and here I should say for all V and V in C. And then finally, this partial composition is associative. So H after G after F is the same as H after G after F for all G, F, G, and H which can be composed. Well, even for all F, G, H in HOM, if they cannot be composed, then just both sides are not defined, and there's no identity. That's it. So that's the definition. And there's a good chance that some of you have seen different definitions, but it's just a reformulation. So, this one has, for me, some advantages because, for example, you could also, in the first place, leave out this axiom here and only impose it when you really. This was not all numbers exist in the lectures. They exist in some notes, but I will not present everything that I was thinking about at some point. So after 1, 2, we will come to 1, 4, which are examples. And I will be brief about that because some of these examples we will use anyway. So we will learn more about them from time to time. And some others we will not use at all, but it's nice to know that they exist. So the very first example is very trivial, namely just take any set as your class of objects and take HOM C only identity morphisms. Then you can check that the axioms are fulfilled. This is not very interesting, but anyhow, you can define it. You can. It is a category. Then there are various categories for which I will try to use the same name during the lectures. So there's a category set. In this case, we have as objects sets, and as morphisms, we have maps between sets. And this is a very natural category. What are the identities? These are identity maps, and we have. Maybe I should need a bit more space, and we take as composition of maps. And this is in a sense not just one example, but there are many derived examples of that. Namely, whenever we have a class of sets with some additional structure or properties, then we can try to make that into a category, and where we simply need maps which are compatible with that additional structure. And as a consequence of that, as is also indicated in the notation here, one often thinks more or less automatically of morphisms as maps between sets, but in the very first example that we had, they are definitely not maps. So in general, they are not. So other examples of this type are a very important type of category that we will deal with in much detail later on, is given some field. I should say when I talk about a field K, unless I say otherwise, I will assume that it's algebraically closed. Just because if you do not assume that, then you have to be careful at some consideration. And actually, I will mention a little bit about that at some point. But usually it will be that. And these are just now I need this space. So here I have K vector spaces. And then I have linear maps between them. And I have again composition. Similar, somewhat similar. If you have any ring R, then the modules over R are a category where you have objects, R modules, and here you have morphisms of modules. And you have again composition. Whenever you have objects which are maps with additional structure, then sets with a different structure, then you have maps with are compatible with that structure and composition. And maybe one more example here. Vect G of K, where G is a group. In principle, any group, but most often this will be a finite abelian group. Then these objects are G-graded K vector spaces. And the linear maps, the morphisms are grade preserving linear maps. Then I will continue with more examples, but actually not all of them. I'm already using more time than I had hoped. And a rather interesting example is a category which I would denote by some special symbol. It has just one object, which I denote by the same symbol, and it has just one morphism, namely the identity of that. Not interesting, but whenever you have a group, or there could be other, it could also be a monoid, or in a more complicated setting in algebra, you can take the category which has just this one thing as an object, and where the morphisms are given by the group G, by the elements of the well, so a morphism is an element of a group, and composition is the group product. And then just for completeness, I will not, just in case I mentioned this at some point. An important category is the category of topological spaces. Objects are topological spaces. Morphisms are continuous maps. And then as a special case of that, you have a category of manifolds of some dimension. Or maybe of arbitrary dimension even, where you have smooth finite dimension manifolds and smooth maps as morphisms. Concerning finite dimensional, very often when I talk about vector spaces, or essentially always, except if I say otherwise, I will actually assume that they're finite dimensional, and I will not use this in the notation usually, because it takes just too much time. Then we have category which is called oriented cohorts in 0 and 1 coalescence. In 1 and 0 I use dimensions. This is just example 1, which we have seen, and there is a generalization of this cobordisms oriented d-1. These are generalizations, and I will say a bit more about them later on. And then there are other generalizations where instead of an orientation, you take some other structure on the manifold. But about those, I will almost not talk. Well, certainly not in the first few weeks. And then finally, and I don't probably write anything about this on the blackboard, but only say it in words concerning class versus set. If you're not careful when working with sets, you can run into trouble. So there's in particular Russell's antinomy, where you say you look at the set of all those sets which are not elements of themselves. And if you now want to describe it, you see that this does not make sense. The way out of that is that you introduce something some people call a universe or a cosmos, where you restrict to a certain class of sets. And you find this, maybe here. I have given some literature on the web page. I will at some point provide a complete list of all those books and articles which in some sense, in some way I mention in the, or also use and maybe not mention in the course, but I haven't managed to do that yet. So here, this you find in McLean's book, Category Theory for the Working Mathematician, standard textbook, and it's section 1.6. And usually I don't use McLean. McLean is written for the working mathematician and not for an introductory course, even though I think you could very well use it for that. I do not usually follow, it would just take too much time. So you restrict to a certain universe of allowed sets, and then, and this would be a definition. You say that category is small if and only if the class of objects is actually a set in the allowed is set in the chosen universe. If one specifies this, they call it U, then one also calls the category U small. But for us, this will be somewhat behind the scenes, but we do not really need it. But it's important, I think, to be aware of the fact that in the definition, you are using class and set precisely in this column. So now we have the definition of category, and we have some examples. Next, like with any mathematical structure, we first can try to look at some structure theory. This is a big word for what I will be doing, and then also about how you can get new categories from given ones. And this will essentially be a bunch of definitions and maybe examples that I will now give one of the after the other. So first of all, there's the notion of subcategory. Well, let's call it S of C, and this is precisely what we think it is. But when you want to make it precise, you have to be sufficiently careful. So let me give you a complete definition. We say that the objects of S, that they form a subcollection of the objects of C, and the same for the morphisms. And then when you have the situation that a morphism with source X and target Y is in S, then also X and Y must be in S. And finally, all the identities must be there. So if X is in S, then you write S just here, then also identity of X is in form of S, and it's compatible with composition. So if F and G are in morphisms in S, then also, well, composable, then G after F is in hom. And there are two important types of subcategories. Well, the first one may be more important, but the second one we should also have heard about. This is a full subcategory. So in general, you take some of the objects and some of the morphisms for a full subcategory. Whenever you take two objects, you take all morphisms between them. So if X and Y are in S, then the hom in S between X and Y is actually hom in C. And then on the other hand, there is a notion of wide subcategory. This is one where you keep all objects, but throw away some of the morphisms totally. Because every category is trivially a subcategory of itself, but we will not be interested in that. Examples. And after the examples, we take a break. If you take the category sets and allow only for finite sets, then this is a full subcategory of the category of all sets. And analogously, you can describe full subcategories of vector spaces and R modules and so on. And another category of abelian groups is a full subcategory of the category of groups. I have not introduced them. These are just objects are groups and morphisms are group homomorphisms. And composition is composition. And as an example of a wide subcategory, which actually is of some interest, is that the category of G-graded covector spaces is a wide subcategory of a category which is often denoted in the same way, but with an underscore, where here the morphisms are all linear. Was there a question? So remember, here the morphisms are the grade preserving linear maps. And then you just allow all maps. Okay, it's 5 after 9. That's no, not after 9, after 3. So we should have 10 minutes break now. But do we leave the recording? Maybe to be on the safe side. If there are questions, we can also take them now. But well, I didn't say this very explicitly. But something. Whenever you have a question, interrupt me.
So this regular category, the vector underline, this is equivalent to the vector, right? To the category vector spaces.
Not really, because it has more structure. I mean, let me see. It has different objects. I mean, the category vector spaces has vector spaces of objects. This category has the same vector spaces of objects, but those the vector spaces together with direct sum composition vector spaces which we say are in grade G.
Yes.
So, for example, super vector spaces is a typical example. If you allow for super vector spaces with both even and odd linear maps between them, then of course, in a sense, they're just vector spaces with all linear maps. But you do not think of an object there just as a vector space, but as a vector space which has a bosonic and a fermionic component.
Yes, but once you have a monoidal structure, they are different, but as a category, they're the same.
Equivalent.
Equivalent.
Yes. But we have to introduce equivalent.
Yes.
But you're right. It's of interest when you have more structure.
Thanks.
Maybe I should make a note about that.
This one is the sufficient by that we have a smaller group.
There was at the beginning a problem that I didn't join the group in the beginning. And when I tried to join, the group was so large that I was forbidden to join.
这可能就是有问题了，因为这个群它在里面，所以很多问题我直接在群里问他。你发你做的语音了？啊？你发你做的语音？我直接瞎做了，我你跟他讲的不一样。然后话筒更尬了。你过来补。是一个我还想去韩国，人力跟这个学领教吃饭做饭。你问哪里呢？我早上这样见到热情在走 France， 能去年。
In the categorical vector spaces, there's one-dimensional space. And Yes, precisely. If you no, if you allow for all morphisms, then possibly. So let's continue. Next, we introduce some special types of morphisms. Say, we have an isomorphism. Say F from V to W. It is an isomorphism if there exists some morphism, say G from W to V, such that if I compose them, I get the identities. So G after F is the identity of V, and F after G is the identity of W. And then we also write G equals F inverse or F equals the inverse. And when if there exists an isomorphism from V to W, which is F, then we also say V and W are isomorphic, and we write this also by writing this sign here, or we just say V and W are isomorphic. And then a monomorphism or also a left cancelable morphism. F is one such that if I have F composed with G equals F composed with H, for arbitrary G and H, where the composition makes sense, then already G and H are equal. And if I do this in the other direction, I get an epimorphism. F. So if I have G after F equals H after F, right? Cancelable, then it forms again H. In the category of sets, a monomorphism is just an injective map, and an epimorphism is a surjective map. And then also in the category sets, you know, if you have a map which is injective and surjective, it's bijective. It corresponds to isomorphism, but in complete generality, you have to be careful with mono, and AP does not necessarily, in some special circumstances, imply iso. Then this definition could have been continued. We say we have an endomorphism. F if the source and target are the same. And we write then for such, say if F goes from X to X, then instead of homomorphism from X to X, occasionally I will write NFX. But it's not much shorter, so I will often not use it actually, but you will certainly see this in the literature. And then you have an automorphism. This is just endo and iso, so an invertible endomorphism. And then a remark, or if you wish a lemma, or if you wish an exercise. Occasionally I will give some explicit exercises. Typically they will be very simple. I will not provide the solution in the first place. If you try to solve an exercise and you do not succeed, just tell me, and then I will take up the solution. But in most cases, it's not really an exercise, not really to solve a problem, but really to come familiar with a notation. The remark is that identities are unique. So if I have two morphisms which are the identity of the same object, they are actually equal, and inverses are unique. And the proof is just the same as proving that the unit element in a group and inverse in a group are unique. And I don't write this down. If you have endomorphisms, then the composition makes this set into a monoid. So you have an associative product in it trivially. Another remark. Often, or almost always, it's not so sensible to say that two objects are equal, but rather it's what is interesting is that two objects are isomorphic. And in particular, very often you deal with two objects which are isomorphic, so it doesn't really matter which one of them you are working with, but you have to take care of or keep track of the isomorphism in order to make certain statements. And by the way, this is something which physicists often ignore. So when in a typical class in quantum mechanics you introduce representations of SE2, then you say there is one representation which is two-dimensional and one which is three-dimensional. But there is one up to isomorphism. Another example is when you have a vector space, finite dimensional vector space, then the dual vector space to that is isomorphic to the vector space as a vector space, but the isomorphism is not canonical. It depends on choice spaces, and therefore it's not of too much interest. So they are isomorphic, but they are not. You should not identify them. You should keep track of the isomorphism. And then a definition which we will not directly use, but which gives rise to some terminology which we will use later, is a split monomorphism, say a morphism from I from X to Y. This is one for there exists a morphism, I call it R tilde, in the other direction, such that if I compose them, R tilde after I, so this is an endomorphism of X, it's actually the identity. And analogously, a split epimorphism R from Z to X, where Z and X are objects. I don't write this all the time. It's one where there exists an I tilde from X to Z, such that R composed with I tilde is the identity on Z. Is this okay? I tilde, no. R I tilde again X. I don't know why I wrote that. And lemma or exercise, and it is not completely trivial, is that any split monomorphism is a monomorphism. And any split epimorphism is an epimorphism. I do not use the definition of mono and epi in their definition, so you have to check it. Also, it is clear that if you have such a combination, say this one I and R tilde, or more generally, I mean it's clear if you take this R tilde, you can take it as an R here, and the I tilde will then be equal to the I here. So always deal with pairs of split AP and monomorphisms, and if we have such a pair, let me write this like that, for a pair of split AP and mono of an R and I, then if you compose them in one direction, you get the identity. If you compose them in the other direction, then you will get an idempotent. So I composed with R, composed with I composed with R is the same as I composed with R, because using associativity, you can use the property here in between. In this case, you introduce the following terminology, and that we will use from time to time. So we call R retraction of I, and conversely I a section of R, and we call, if you have this situation X and Y here, the Y a retract of X, and I will not use this very often, so I don't write it. We say also that if we call this P, then I and R are a splitting of the idempotent. We will talk about split idempotents later on. This notation.
And so it's not true that every monomorphism is split. Or every epimorphism.
No.
You have an example.
I cannot give it right away. Well, we will talk about exact sequences a bit later. So if an exact sequence does not split, then if you have an EP and a short exact sequence, then they are not split.
So this for this terminology, this is only for the split.
This is for the split case. I said in words, in this case. So when we if we have I and R, such that
both are split.
So yes. I did not say this. This would be another part of the lemma. If I have a split monomorphism, there exists certain R tilde. This R tilde will be a split epimorphism because the equality here we can use as the equality here.
So if the R and I sequence will have a tilde in the terminology.
Once I'm at this point, I see that these things always come in pairs. Then I just call them R and R. Then very briefly, I'm not really sure whether this will play a role later on, but I think you should have heard about it. We have, of course, we can check equivalence. It's an equivalence relation. Otherwise, we would not call it like that. But there's another interesting equivalence result. Isomorphism is an equivalence relation. If X is isomorphic to Y and Y is isomorphic to Z, then X is isomorphic to Z, and so on. But there is another equivalence relation which is of interest in some situations. We say you have a finite zigzag. I'm not sure whether there are other terms for this between two objects, say X and X prime. This is just a collection of morphisms of the following type. You have an F0 from X to some X1, then you have an X2, and you have a morphism F1 from X2 to X1, then you have an F2 to some X3, and so on. And this ends up with some xn minus 1, and then you have an xn, and the xn is equal to x prime. And lemma existence of finite zigzags between x and y is an equivalence relation. I should say we always have a morphism here from left to right and then right to left. Of course, this is without loss of generality. Yes, there are two arrows in the same direction after each other, then we just compose them into a single one. Then this will be of the same type. And one says that x and x prime can be connected in C, and we call the equivalence classes path components. And the set of path components is often also denoted by pi 0 of C. I don't write that. Example. Remember example 1.1. In this case, we have that so the two zero-dimensional one manifolds y1 and y2 are connected or can be connected. It simply means that there exists a one manifold or a configuration, I called it, such that let's call it X, such that the boundary of X is y1 bar disjoint union with y2, where y1 bar is y1 with the reverse orientation. And example for that is assume you have plus, minus, plus and minus, and you look at this configuration. This is a possible configuration where the boundary of this one manifold here is consists of this zero manifold and this one, and orientations fit together with what is required here. So this zero manifold and this zero manifold are in the same path component. And then as an exercise, you can convince yourself that the set of path components here is isomorphic to the group of integers. And you can also ask what are possible generated, if you write this as generated by one element, really big group generated by one generator, what the possible generators are. And you can ask what would you get if instead of oriented manifolds you get you take unoriented manifolds. As a side remark, which I don't write down because everyone knows this, is that instead of equalities between morphisms, very often we draw commutative diagrams. So we have, well, for example, say instead of writing the names of objects, I just do a dot. But this would be some x, y, and so on. F, G. If I say H is G composed with F, then it is the same as saying that this diagram commutes. This is a completely trivial case, but often we draw more complicated commutative diagrams, and then an important tool is to show various identities by looking at complicated diagrams and splitting it up into subdiagrams, using that, showing that they commute and then some of this commute. But I will not typically use this. Instead, very often and I will come soon to that. I will use some graphical calculus to describe the morphisms. But before that, one more thing, that's the last part of basics. Three simple possibilities to get from one or two given categories to new ones. The opposite category denoted by C op. Maybe with two keys, or maybe stands for operator or something, is the category which has the same objects. And with the morphisms in C op between X and Y being given by the morphisms in C between Y and X. So you reverse all arrows in between objects. And then composition, F, opposite composition with G is G composed with F. Regarded as a morphism in C op. Then there is the notion of Cartesian product. Of two categories, C1 and C2. This is the category where objects are pairs, say x1, x2, where x1 is an object in C1 and x2 is an object in C2, and analogously for morphisms. The morphism is a pair of morphism, say F1, F2, where this will go from say where F1 goes from x1 to x1 prime in C1, F2 goes from x2 to x2 prime in C2, and then this morphism in the Cartesian product goes from the pair x1, x2 to the pair x1 prime, x2. And finally, third is disjoint union. Usually one uses these terms just without explanation and assumes that everyone knows what is meant, but I think this spelled out. C1, C2 of the categories. In this case, the objects are just a disjoint union of the objects of C1 and those of C2. It may be sensible to look up the explicit definition of disjoint union of sets. And the morphisms are the following. If X and Y are both in C1, and the morphisms between them are just the morphisms we have in C1, and the same if both of them are in C2. And empty set else. There are just no morphisms between objects here and objects here. And then concerning opposite category, as we will see some examples of, whenever we have an interesting concept for a category, we can formulate the same concept in terms of the opposite category and get another interesting concept for our original category. And one often says that one has a dual formulation. So duality in this context is meant in this sense. And we will see examples for that. Now we come to 1.3, which is about graphical string calculus. And this is a tool that we will use in much of the course, not in all. It will become of interest for monoidal categories and then to some extent module categories, also higher categories. For categories in themselves, it's not of interest, but I have to introduce it here first. So what we do is to describe morphisms in terms of some kinds of strings or wires, and we simply say that objects corresponds to strings or wires or edges of a graph, and morphisms correspond to gates, if you think in terms of logical structures, or I will use the term coupon. Actually, this is just something one-dimensional, and this will be zero-dimensional, but we do not draw it zero-dimensional because it's it makes things often easier to grasp when we with that. So if we have a morphism f between x and y, say, then we take a box or coupon, and very often they are drawn as rectangles. I draw them slightly deformed in order to make clear that a morphism has an input and an output. And for me, inputs will be on the bottom and outputs on the top. Then I write the source at the bottom and target at the top. And in principle, I could draw this also in this way. This would be maybe more logical, but as I said, it's easier to see what is going on in some respects by using this notation. And there's in particular the identity morphism. For that, we simply leave out a coupon, or here. Or this identically just as a line, labeled X. And also, I draw typically these lines vertical from bottom to top. What is important is that they are that they are progressive graphs in a suitable sense. You are allowed to deform this by what you would call ambient isotropy, and you can define that, but I will not do it. It's just instead of having a straight line, you could have something like that. It's precisely the same thing. So you could introduce an equivalence relation on such graphs, but I refrain from that. If you want to look at the details, you can look at the original paper by Royal and Street, but I don't even cite this here for monoidal categories where this becomes important. Now composition. corresponds to the following. Say we can compose G after F. Then we would write this also in this way. And you should really think this as a move on graphs. So you start with this graph and you replace it by a different one, and then you require that they are equal. The point is that you can use this now locally in any complicated graph as an identity. And with this, for example, the associativity amounts to a sequence of moves. It's rather trivial, but I show it anyhow. So if you start with H after G after F, then by using this move here, we can draw this as H and then G after F here, well, other way around, but since I'm drawing from bottom to top, I have it's easier for me to formulate things. In the literature, I should say, there's also the other convention that you go from top to bottom, and in some cases also from left to right. For example, in this example 1.1, it was just easier to draw for me by drawing from left to right. Now we use again the local move here to draw this coupon as a sequence of two, which are labeled by F and G. Now we use the local move here again to combine these to H after G. And then you use again your local move to write this as H after G composed with F. And then, in a sense, associativity of the composition is trivial, but it's encoded in the conventions together with the fact that you allow for some local moves. And this is, and the same thing you can do for identity. As I said, this in itself is not of very much interest, but once we come to monoidal categories, it will be important to have this as a tool. And this is already, for now, everything about graphical calculus. I will call it graphical string calculus. Some people use this term. There are also other terms. By the way, the fact that this is a sensible tool can be seen from the fact that in the literature, the graphical calculus for monoidal categories has been invented in various forms several times. And of course, this can be used directly for categories, but then also it has analogs in flowcharts for computer programs, electrical circuits, and so on. And the various areas actually can be used to get some ideas in other areas via calculus. That is, I think, an important aspect of this graphical tool. One before it's just as a short interplay. It's just one example, but because it's an important example, and also in applications very often one does not spell out the definition in detail because everyone is supposed to know it. I give it here separately. So this is the following definition. We have a category. I already used the name for this cobord oriented DD-1. Where D can be 1, that was our example, 2, 3, and so on. This is the following category. Objects are closed, oriented, smooth, D-1 dimensional manifolds. Let's call them M and similar. And then morphisms. A morphism, call it B, from M to N, is a class of cobordisms from M to M. Where cobordism, I don't write this, is again oriented, smooth, now d-dimensional manifold. Which can have a boundary and with an orientation preserving diffeomorphism. I call it phi M, phi B, from the disjoint union of M with reverse orientation and N to the boundary of B. And then when I say class here, I use an equivalence relation. Which is the following. We say that B and B prime are equivalent if there exists an orientation preserving diffeomorphism. Let's call it F from B to B prime, such that the following holds. The following diagram commutes. So we have let me see. I again made a mistake here. If we take this M bar, this one union with N, we have two diffeomorphisms here, which are phi B tilde and phi B prime tilde, where the tilde means it's the phi B, which goes to the boundary of B, and then the inclusion of the boundary into B. I don't write this explicitly. The composition of phi with the inclusion map. And we require that this commutes, and if such an F exists, then we say the two are equivalent. So this in particular means if you do some deformations, then as a cobordism, they are considered to be the same. So these are the objects, the morphisms. What do we need else? We need identity morphisms. identity on D-1 manifold M is just a cobordism which is given by, well, which is represented by what is called a cylinder over M, which is just M direct product with an interval. Together with, of course, M bar is diffeomorphically given by M and on one end of the cylinder and M on the other end with appropriate orientations, and then composition is gluing along the boundary. Well, along part of the boundary. So we have B M prime, say B for B prime for, let's say, B going amorphism from M to M prime, and B prime from the same M prime to M double prime. This would then go from M to M double prime. And here one has to be more specific, and I suppress almost all details. If you take two smooth manifolds, let's say I argue with one-dimensional manifolds, say circles, and you have two manifolds with these circles boundaries. If you glue them together, if the two separate parts of which are two manifolds are smooth, what you get is not smooth. But what you do is, instead of gluing along a circle, you really take a small cylinder over that circle, and then on your other side you have the same with opposite orientation, and you identify these as colors. Now, this is not all to be said. You can do this, but there is no canonical way to do it, and then you have to show that this is not a problem. And in the two-dimensional case, so cobord 2,1, this is described in much detail in the book by Koch, which is called Two-Dimensional Topological Field Theories and Frobenius Sammanfass. And for higher, for the higher cases, actually I'm not so, I cannot give a good reference. Morally, it's the same as in two. Oh, and this is a bit too early to stop, but let's have the break, and then I still have to continue with the program. Any questions in the break? I have a question on my laptop. This, unfortunately, the cable is not long enough. Someone sent a message. I said it will be enough. But wait, I think someone sent the message. What? Are there questions? Or what? Yes. That is recorded now. Camera is not quite focused. That's okay. No, it's not focused. Okay. 1, 2, 3, 4, 6. I thought it was 7, but I know there's one. Okay. Okay, to continue, I will give you a particular example of equals 2, so cobot 2, 1. And one reason for that is because it's a nice result. Another one being that I already mentioned in the d equals 1 case that in that example we have more structure than just a category, and actually this is true for higher views also. From what I will do now, it's actually easy to see this, even though I will not point out explicitly. So what is in d equals 2? An object is a finite disjoint union of oriented one manifold, a finite disjoint union of circles. And I will not draw the orientation of the circle. Then we have morphisms which are coordinates between those. And now their result is that there are 6, even less, elementary morphisms from which all others can be obtained by a combination of gluing and disjoint union. And these are the following. This is called the cup. So this goes from the empty set regarded as a oriented one manifold to the circle. No, sorry, this is called a cap. And then there is a cup. No, this should be called cup. And this cap or opposite cup, which goes in the other direction. And then we have what is called a trinion, or also pair of pans, which goes from S1 across S1, or disjoint union with S1 to S1. And then there is the opposite trinion. I don't write the term here. It just goes in the other direction. And then there is a cylinder, which goes from S1 to S1. This is just the identity. And usually when one talks about generating objects, then one would not count identity separately. But it's just nice to take it to include it, and that's maybe the main reason why I'm drawing that. What is sometimes called exchanging cylinders, which is drawn, which I would draw like this, which is not an optimal way to draw it. And so this goes from S1 across S1 to this joint union to S1. What is bad about the drawing here is that it somehow seems that this cylinder is over the other cylinder and not under. But this is just an artifact of drawing this on a two-dimensional blackboard. If you do this three-dimensionally, you can go from different angles, and you see there is no one preferred over the other. And if you want to do it exactly, what you really should do is that you have two cylinders. And remember, the cobordism is not just a two-manifold with these boundaries, but it comes with a diffeomorphism, in this case from 2 copies, well, altogether 4 copies of the circle. And you now say they are embedded as in this way. Well, so you do not have to draw it like that. And you can do this in terms of some explicit formulas for the diffeomorphism, and then there is no need for drawing. But since you see such drawings quite often, including this one, I think it's worth pointing this out. It's, by the way, not so difficult to allow also not just for one manifolds, closed one manifolds as objects, but also one manifolds with boundary. Then the objects are disjoint unions of circles and intervals. And then, of course, there are more possibilities, but again, there is a small finite number of generating morphisms. Now we could come back to the more theoretical development. Now we talk about functors. And when we deal with a category, we have 2 layers of structures. So if we want to relate 2 different categories, we have to account for these 2 layers. And accordingly, we have the following definition. A functor often denoted by capital F or similar letters between 2 categories, C and C prime, is the following. We have the data, which are 2 maps, one between objects and one between morphisms. And both of them we still call first F. And then this should be compatible with the structures. So we have as axioms that if we apply the functor to an identity morphism, we get an identity morphism of the object on which we get from V by applying the functor for every V in C. I don't write this out. And then we have that we preserve suitably source and target. So the source of f is the same as f of the source of f, and the same with t. And finally, compatibility with composition. So if we first compose, assuming these are composable morphisms in C, and then apply F, it's the same as first composing, first applying the functor individually to the morphisms, and then composing. So I should write the prime here, maybe that's the composition in C prime. Connect the definitions. We say we have an Endor functor. If we have a functor f where we have C prime equal to C, and sometimes, but I will try to avoid this, instead of functor, one says also covariant functor, and then a contra variant functor from C to C prime is the same as a functor, a covariant functor from C opposite to C prime, or also from C to C prime opposite. That's equivalent. And examples for functors, of course, simple examples, and then we will get more complicated ones later. First of all, there's the identity functor, which I will denote this way typically. So this just maps every object to itself and every morphism to itself. Then there are various types of forgetful functors. Namely, when we have some structured set and forget some of the structure. So, for example, we have a forgetful functor. Often they are denoted by U. If we take the category of groups and just forget for each group that it's a group and only take the underlying set, then we get, then this is functors where morphism of groups is just sent to the map between the underlying sets. Then another functor, which we actually already have used, is the Hom functor. Namely, we can take the Cartesian product of C opposite of C to Z, where we map a pair of objects to the morphism between them in C, and analogously for well, let me just write it like that. I have not used this notation before. You must say that. What do you mean by that? If you take any morphic, well, maybe I write this down. If you have any H in from C of G, then you map this to G after H after F in from C prime, X prime, and Y prime, and what type of morphisms these are you get from making sense. Then another example, I don't write that down. The time I already mentioned that to every vector space, there's a dual vector space, or the space of linear maps from the vector space to the underlying field. And if you take this as your map on objects, there is a corresponding map on linear maps, which makes this into a functor, which is called the dual vector space functor. And then more interesting than doing this once is if you do it twice, you have double dual functor, and this is more, which is an endofunctor. If the vector space is finite dimensional, then you can canonically identify the double dual space. Then we get an endofunctor. Now, I said we have two levels of structure for categories, and therefore when we now define a mapping between categories, there are two levels. But we also have two levels of things that we can do. Namely, we can also now ask how can we relate different functions between the same pair of categories, and that we call a natural transformation. Say eta from F to G, where F is a functor from C to C prime, and G is a functor from C to C prime. And what is this? This is a family eta X of morphisms, which are indexed by the objects of C, such that, so eta X goes from F of X to G of X. So this is a morphism in C prime, such that the following diagram commutes. Now I use actually a commuting diagram. We have two possibilities to go from F of X to G of Y. We can first apply eta X, then we come to G of X, and then we can apply G of F, where F is any morphism from X to Y. Or we can first apply F, the functor F, to this morphism, and we get to G of X, and then we can apply eta Y. And this diagram should commute for all morphisms in C. We also say that this eta X is the component of the natural transformation at the object X, and then we say that we have a natural isomorphism of functors. Is the same as a natural transformation for which all components are isomorphisms. Sometimes, but this will not happen very soon in the course, is that we describe a natural transformation by a pasting diagram. So we have our categories C and C prime. We have our functors F and G between them. and then we take our natural transformation from F to G. We draw it here like with a double arrow. And sometimes, well, actually, depending on the context, very often one writes a double line arrow for natural transformation. I will not usually do that because if I tell you that I talk about natural transformation, you already know what I'm talking about. As a remark, functors if C is a small category, and D is any category, not necessarily small, then there is a category which we call the functor category from C to D, where the objects are functors from C to D and the morphisms are natural transformations. And a short exercise is to check that this way you really get it. A few examples of functors. I want to guess, maybe not all that I have the list here. This is this was actually wrong. This was two. Examples, some interesting functors, and here I use it's in 6.2 of this book by Adamek and two others, which, by the way, is freely available on the internet. So that it's a nice book. It's called The Joy of Cats. With some subtitle. Yeah. There is so-called squaring functor. Which goes from groups to sets, which takes a group and maps it to the Kronecker product or Cartesian product of the two of G with itself, regarded as a set, and analogously for maps, for morphisms of groups, just to morphisms of sets. And then if you take the product in the group G, which I denote by mu G, as component of a natural transformation, then this well, as an ansatz, then you do get a natural transformation from, this should get a name maybe, SQ for square, from the squaring functor to the forgetful functor. And you can write down the naturally, that's an exercise, naturality condition, and check that it's indeed satisfied by using properties of the two product. And instead of groups, you could also use algebras here. Then in the another example, I mentioned that you have the double dual of vector spaces, and said that you can identify this with the vector space itself. But remember, I already pointed out it's never or not often a good idea to identify things, but you have to take care of isomorphism, and correspondingly, you have a natural transformation, eta v. V is a vector space. Goes from a vector space to its double dual. And we define it simply by what we use in order to identify the double dual with its with the vector space itself. So eta v of a vector in V, if you apply this to F, well, we think of the double dual as the dual of the dual, then this is just F of V. And this gives a natural transformation of the identity on vector spaces to the double dual functor on vector spaces. Then constructions, I don't write that down. Constructions you have in algebraic topology, in particular the nth homotopy group and the nth homology group. These are also functors from topological spaces to groups, and you get actually a natural transformation from homotopy to homology. This is called the Prerequisite homomorphism. So this is indeed, as you can check, a natural transformation between those two functors. And then there is a simple type of natural transformation for Hom functors, namely if you take any morphism between two objects V prime in a category C, and you define Hom V. When I write a minus sign here, this is a placeholder, so it just stands for an arbitrary object to morphisms now from V prime to any objects, which sends a morphism H in this space to H composed with F. So you first go from V to V prime, and then from V prime by H to something. This is a precomposition. And also there is a corresponding postcomposition. where you send any G to F after G. These are natural transformations of N functors. And the final thing, remember this category 1 object and the morphisms given by the group G, by some group G. If you have then if you have a functor from this to vector spaces over some field K, then you can convince yourself that it's the same as a K-linear representation. Of G.
Yes, you should remove the final.
The
second example.
Yeah.
The V prime, I guess. The
second V prime. V. No, wait. I should get it correct. F goes from V to V prime. So so this is correct, and G goes from let me see, F goes from V to V prime. So then I have to write prime. Yeah, like in my notes. So if I now have two such functors, I have two K-linear representations, and you can convince yourself that a natural transformation between such two functors, it has just a single component because it's only a single object. Then this is the same as an intertwine between the two group representations. So a map of representations. Who knows? Who is using the term intertwine? Is you familiar with that term intertwiner? Because some people are using this and assuming that everyone knows, but then I have met others who never saw the term. They will say morphism of group representations. Not final. Those two final things that we will do is an important result. Which can be formulated in various equivalent ways. 146, and which is used in many proofs. This is called the Yoneda lemma. So, like it's called a lemma because the proof is not so hard once you know it, but it's really an important result. And it says the following: consider a functor f from a category C to sets, category of set, and consider an object V in C. Then there is a bijection between two sets, namely the natural transformations which I denote by this, from the Hom functor in C between V and something, and the given functor F to just F of V. So by definition, F of V is in C, so F of V is a set, and this is a set, and the statement is then in bijection. So maybe just indicate how you prove this. So to get you get a map in this direction in the following way. You take a natural transformation in this set, and you map it to an element in this vector space, which is the following. You take eta, the component at the vector space V, and apply it to the identity of V. This by definition is an element in this set. Because well, what is eta V? Eta V goes from endomorphism of so you put in V here, and then you have F of V here. So this is a morphism from an element from an endomorphism space here to F of V, and you apply it to some element here, so you get an element in F of V. And in the other direction, you start with an element I call Y in F of V, and you map it to the natural transformation eta, for which the component eta at some object X in C is the following map. So it goes from Hom Vx now to F of X, which sends morphism here to F of F applied to Y. So F of F is a morphism, is a linear map from F of V, vector space F of V, to the vector space F of X. And you apply this to the element in the first vector space. And then you show that these two maps are mutually inverse. Just compose them in both directions, and you get this. And now there is also some kind of naturality property of the construction here in the two arguments that we have here. And a remark which I don't write down is that actually this does not hold in full generality for arbitrary categories, but only for so-called locally small categories. But I haven't defined that, so this is one of the things I will not go into. And for details about this for more details. There's the book by Rio. I think I have mentioned this on the website. It's called something with categorical.
You wrote the natural transformation that you do. So it's well defined, it's unique. There is only one natural transformation for which it exists.
Well, I have here a prescription for a map from here to here, and I have here some prescription from a map from here to here, and I claim that with these two prescriptions, the two are mutually inverse. So, is your question?
The natural transformation.
Well, I describe here what the natural transformation is. So I have to map this to a natural transformation, and I have to tell you which natural transformation that is. So there means what I have written here, eta x for all x. For every x in C, I take this description. There's an important special case. Namely, take f itself to be a home functor. Or some other W, say. And what we then get is, when I don't write it down, you just insert here for f this home functor, and on this side, what you get is the home functor W to something evaluated at V. So this is just the set hom C WV, and so we have a bijection between natural transformations between home functors and again a home functor, namely the home functor between the two objects which define these home functors. So here we have the home functor for W, and here we have for V. And this can be used in various situations to detect that there are isomorphisms between objects. And also it allows you to regard the opposite category as of C as a subcategory of the functor category from C to Z. Namely, look at the functor which sends any object in X to the corresponding home factor here. So home C X to something. So for any X in C, I get this home functor, and it's the opposite here because this is in the contravariant entry of the home functor. So, and And this is also called the Yoneda embedding. So if I have a category, then there is a larger category of functors in which the original category is naturally embedded. And we have 1 more minute. That's enough for one more definition. We say we have an equivalence of categories, C and C prime. If there is a functor AF between them, such that there's another functor H, say, in the opposite direction. And now you could say they should be inverse. So if I compose them, I get identities. This is too strong a requirement in general, but there is a weaker form, namely there are natural transformations. Eta from the identity of C prime to the composition of F with H, and epsilon from the composition of H with F to the identity on C, identity functor, which are in fact natural isomorphisms. So if I compose them, they are not the same as the identity, but there is a natural transformation which is invertible. And in this case, we have in this case such a thing exists. We say the two categories are equivalent, and I will denote this by the symbol. And again, you can check this is indeed an equivalence relation. And the time is over. So thank you for today. We have come to 1.5. I said I have 12 subsections for chapter 1, so we will not be finished this week with chapter 1, but sometime next week. Thank you. And then maybe someone has to help me to start the recording. Yes. Yeah.